So this morning we discussed divisors. And we talked about, in particular, well, two types, and we talked in particular about Cartier divisors. What that means is that you have a covering in your space, I'm just reviewing what we said this morning, and on each open set you have a meromorphic function. And on the overlap there's some compatibility conditions, so m alpha over m beta, of course let me emphasize only overlap. Then you define this thing to be f alpha beta. This is a homomorphic function which doesn't vanish. This means the polar set and the zero set are defined with multiplicity by these functions. Okay. So please notice the obvious fact. F alpha beta, now I'll change to the notation this morning, say f I ij, is a mapping from uij to gl1c. It's a homomorphic function which doesn't vanish. Right? This is C star. And you can notice the two conditions that this is automatic given a divisor. That the inverse is fji. And the second condition of compatibility on the threefold overlap, and the fij f.
So you mean locally?
Huh?
There is no fij is not a bijection. Locally you mean?
What did I just say?
Fij minus 1 is just locally, no? It's a number, Fij minus 1.
It's 1 over fij.
Yeah, I mean, it's not an inverse map.
Yes, it is. Oh, I see what you're saying.
I think you mean fi from ui to gl1 and fij is like.
So fj, yes, that's right. So is there some confusion here? I mean, I really mean, so f alpha beta, f beta alpha, if you like, is from u beta alpha. I mean, regarded as a map. What's the confusion? I'm a little bit confused with the confusion.
I mean, Fij minus 1 is not a map from C star to beta alpha. It's just a number. It's
Fji is a 1 by 1 matrix.
yeah, it's a number. It's not.
It's a 1 by 1 matrix.
No, I mean the question is what the inverse means. So it's not the inverse of a map. I mean it's not the inverse of f alpha beta as the map, but it's the inverse of
Of the matrix.
the matrix.
Locally.
That's what it means. It's
Yeah.
the inverse of the matrix.
No, I'm good.
Right? It's the inverse of the matrix, which is so degenerate in this case because it's just a 1 by 1 matrix. But it really is the inverse, right? I mean, if I have a 1 by 1 matrix, the inverse of it is 1 over it. Right? That's what I mean by here. Okay, but thanks for mentioning this. I would not know that. And this is automatic. I mean, you just check the fact that this is a ratio like this means these two conditions are fulfilled. So this is true. Okay. So recall the business about vector bundles. If you have mappings in a GLN which satisfy these conditions, you get a vector bundle.
Yeah.
It's the same thing. Now these happen to be 1 by 1 matrices,
So we get a line bundle.
so we get a line bundle. So we get a line bundle. Let's call this divisor D. divisor, and that defines then a line bundle, and we denote that by L of T. So this is a line bundle. So associated to every Cartier divisor, in a very general setting, we have a line bundle. Okay? And now, let's think about this for a minute. The notation, I will always use say over X, over U, it doesn't matter, of the line bundle. So this is space of sections. Of LD. So what is a section? So you can say, well, here's a line bundle, and here's the base space, and here's X, and here's L, LB. And the section is just a map into the bundle space, which is a section, holomorphic recorded. And that's the geometric picture of this.
It's just a homomorphic map.
Huh?
Isn't it just a homomorphic map?
Just a holomorphic, of course, you go up and down and you get the identity. I mean, you're not mapping a point over here, you map it into a point above, so it's saying, right? So, up and down equals the identity. Here's the zero section. Well, this thing is locally trivial, so on some local trivialization here, UI, maybe let's say the same one we're dealing with here. Here's a local trivialization. So, as you know, pi inverse of UI, in a good way, is UI cross C. And at this level, this section, from UI to UI cross C, only localized and in local coordinates, this will be a section which we would call SI, over the UI. Okay? Over the UI. So here is the area of local trivialization. We regard it as UI cross C. We look at it with a microscope and it's just a mapping in there. Yeah? So this is, well, maybe I should write it very precisely, is this point X here goes to X SI of X. And of course, you have a compatibility condition. And the compatibility condition is a stupid condition, namely SI equals Fij Sj on UIJ. So it has to, we've cut this thing apart with trivializations, and they are compatible in GL1. And GL1 is just a multiplication here. Simple-minded thing is that. So it says that a section in this bundle over X, using the trivialization, is the same thing as Sij as above, SI as above. Functions satisfying compatibility conditions. Okay? I emphasize SI are holomorphic on UI, so really holomorphic section. So maybe if there's any confusion, I will write O here.
So is there any link to the vector field? Like a section defines a vector field on a
On
tangent
the vector bundle, yeah, sure. And if you had the tangent bundle here, the holomorphic tangent bundle, a section would be a holomorphic vector field. And you will see, by the way, I mean, you know, if this thing's a Riemann surface, right, smooth, then its tangent space is one-dimensional. So its tangent bundle will be a line bundle. The holomorphic tangent bundle will be a line bundle of fundamental importance.
But this, the bundle that they generate, is a bundle of vectors, of functions, of what? When, I mean, you started with the Cartier divisor, and we saw in last course that you can, like, you start with a tangent bundle, but you can exchange it with a cotangent bundle, with everything. You can put endomorphism, you can put, what is this LD? Is it a, I mean,
Let's look for a moment, okay?
yeah.
Let's look for a moment. So recall here, we started with this Cartier divisor. So the Cartier divisor satisfies this. These things are meromorphic, so they could have poles. And now if we have a section, we have this. Okay? And now you notice, and this is just a convention where I put things, but please notice this. So on the overlap, these things agree. Okay? So a section gives us a globally defined meromorphic function, let's say ms. That's interesting. So what are these sections? What are these functions? The divisor of ms, and I'm going to write something, you're going to ask me, what the devil does that mean? The divisor of this ms is bigger than or equal to d, minus d. It'll take us a minute to get through this. Let me write it first. Okay. This is just notation, but it's important notation. So, given a Cartier divisor, we have Fij's. Given these Sij's with this condition, you have a line bundle. Given a line bundle, we have the space of sections. Given local trivializations, we can write the sections as just functions, which transform right. They transform the same way as the given Cartier divisors is. Notice, however, you don't know anything here about polar or anything. You just notice this. Okay? Now so to get, the key thing is that on the overlap they agree, and so we get a globally defined function. Well, if you have a globally defined function, you have its divisor. That's what we're talking about this morning. Global or local, I don't care. Globally defined function, you have its divisor. Right? This has its divisor. So that's its divisor. What does it mean, bigger than or equal to minus d? Well, it's the statement that it's purely the statement that this function, this function is bigger than or equal to minus d. Well, let's see if I can get it right. This function times mi over si is holomorphic. No, I don't want to do that. This is what I want to do. Have I got it right?
Because that's
Yeah, this is holomorphic, right? So this has certain poles. That means, did I get this right? Mi times this thing is holomorphic. Okay? Right. That means the divisor of this thing, which is the divisor, if you just look at these things add, it's a group, is bigger than or equal to 0. Bigger than or equal to 0 means no poles. Okay? Okay, so if you look at what the group thing means here, it means that this thing is bigger than or equal to minus d, this thing. Which I just wrote it for mi, so that's minus d. Okay? So if you look at what I just said, you look at what I just said, then there is an isomorphism, and you can do this on any open set between the sections of this bundle on this open set and the meromorphic functions on this open set which I will call MD, no, well, I'm gonna call this thing OD of this open set, which is equal to the set of meromorphic functions on X, such that the divisor of M, and now this is the divisor of M, is greater than minus D. Let's go through this. If I have a section, I build a meromorphic function, just like this, a global thing. Okay, that's already good. The thing is that I have a new divisor here, not the same one, mi, the one over mi, because I put this on the denominator, right? So this divisor, if the original divisor, this divisor here, let's say this thing, whole thing, the divisor of this thing, I'm going to call D. Then here it's 1 over D, but I mean that we write that additively and write that as minus D. So zeros have gone to poles and poles have gone to zeros. So, and this thing that we have here,
So how do you count D? You add D, you add 1.
say it again.
How do you count D?
D is the divisor given on the covering by the meromorphic functions mi. Okay?
So is the number or?
Hmm?
It's a number or?
No,
It's a very divisor. I mean,
it's a Cartier divisor. It's this collection of meromorphic functions satisfying this compatibility condition.
Okay.
Okay?
I think the question is how do you add two divisors?
How do I what?
Add two divisors.
Oh, that's right. It's a convention. So, okay. Yeah, you multiply. So the thing is absolutely right. The confusion is what happens here. Yeah. So
And
let me clarify this. This is of course you're absolutely right in asking this
So,
question.
so the point is unclear, how do you do algebra on divisors, and the second, how do you order?
Yeah, exactly. So Thane was asking a good question, and you were confused by my situation here. So let's go. So suppose you have mi and say another one m hat I hat. Okay. Two divisors. Then of course you have this one. Right? This is what you meant, I think you multiply, obviously you multiply, what you're doing here though, is, okay, if this thing is called D, this is an abelian group on the divisor. This is called D, and this is called D hat. Then the notation for this divisor is D plus D hat. Okay? And it makes sense in some sense. You can see why it makes sense because, for example, on a Riemann surface, if you have n1 p1 plus n j pk, j, say k, that's maybe a divisor on a Riemann surface called D, and you have another one called m1 q1 plus, this is a notation of Riemann, and see, these are, it's really the Weil divisor notation, right? So points and multiplicities, although it's here definable by meromorphic functions. So points and multiplicities, you write the Weil notation, you get the divisor D. It's additive notation. You do this thing here, you get the divisor, oh, I'm sorry, this should be Q, and this should be maybe QL. You maybe get a divisor D hat. Right, and you add these things, and this is the notation here. Okay, I mean, an add means you just have the various points and the various multiplicities add. So it's just a free abelian group generated in that way, right? So thank you, Thane.
But can it happen that they cancel?
Sure.
And it's no problem if they
No, just add. It can happen here
So
too.
it's just
I mean,
notation.
canceling can here happen. I mean, you might have some zeros here that get killed by poles here. Why not?
So the ordering is, let me guess, like if it is holomorphic, then it is greater than 0.
That's right. That's right. So, okay? So I was much too fast here, and I appreciate the thing in particular. That's the point here, right? So that's the divisor of the globally defined meromorphic function times the divisor defined by the ME. This convention says you should think of these as Vey divisors and add. And the convention is, as he just pointed out, that that's bigger than 0, so this is bigger than minus d.
Professor, is it really divisor or the degree of the divisor? I mean, you sum the coefficients and...
No, that's just the divisor. Degrees, of course, are gonna, okay, so, of course, you will have degree.
I think you compare the degree, but how do you compare divisor? Because divisor is an element of the free abelian group, and how do we order them? That I don't know. So what is the order in
No, I just say that, so, okay, definition. D is bigger than 0, if and only if, bigger than or equal to 0. It's what Thane was saying, if and only if the MI are homomorphic. Okay.
But then how do we move this thing on the right side?
You check it. Check it. So that, oh, okay,
So the
so,
equality is the equality happens when the functions are constant only.
yeah, what is the 0 divisor?
I mean, if d is equal to 0, does it mean that
So this,
everything
this,
is
yeah, this is the question, what is 0, right, in some sense. So this 0 means the MEs are neither, okay. So these are units, so they don't have any zeros or poles. Okay?
So we compare divisors with this criteria.
Yep.
Okay.
Is it totally ordered?
Hmm?
Is it totally ordered? It's
What does that mean?
is it a total order on
I mean, can you compare any two divisors?
Well, what you're saying is if you're giving me D1 and D2, you want to compare these with this order?
You cannot.
No, of course not. You just know, you have this abelian group and you know what's bigger than 0 and what's less than 0, that's it. And of course, okay.
But can you quantify the number of poles?
Okay, so that's what Latif was saying. So what you can do here is you can take degree of the divisor, right? And what's going to happen is you're going to have zeros and poles, and some's going to be you're going to add all these things, right? For a Riemann surface, for example. Okay, you have to think in a higher order what that really could mean. But for a Riemann surface, you can at least add these multiplicities.
Yeah, but
That's what you were thinking
that's
about.
bad. When you multiply, you lose. I mean,
You're losing a huge amount of information.
Yeah, when you multiply.
But it's an invariant, at least for a Riemann surface, it's an invariant. Okay? Any other remarks? You okay? No.
I'm okay, but I'm just trying to think if it is a good order in some sense.
No, it's only the statement. It's only the statement is, so D1 is greater than or equal to D2 means D1, this is the definition, D1 minus D2 is greater than or equal to 0. This means the meromorphic functions defining D1 divided by the meromorphic functions divided by D2 are holomorphic. That means the zeros of this thing are contained in the zeros of this thing, right? And the poles of this thing are contained in the pole of this thing. They cancel out. That's all I'm saying here.
Up there, is it just a typo that we put greater strictly than d minus d?
I'm just not hearing very well.
Is it a typo up there when you put strictly greater than minus d, or?
Yeah. Right. That's what you meant, yeah.
Yeah.
So again, it's a confusing thing, but I think it's worth beating our heads against a bit. If you start with the Cartier divisor, and then you have some section in the bundle, you make this meromorphic function. Vice versa, if you have a meromorphic function of this type, you can just work backwards and get a section. Okay? So these are the same things. Okay? So it's a very interesting thing, right? It's global existence of certain kinds. We'll have statements here about global existence of certain kinds of meromorphic functions. Okay? Maybe it's a little confusing. I'm sorry if it is.
Well, for me, it's not surprising that we talk about global things, since sections are still global.
That's right.
We have global things in the right and global things in the left, because sections are still global. So
That's right.
there is no movement.
That's right. That's right.
Everything is global.
You should think of a Cartier divisor. It's global in some sense because it's defined locally, but it's a global thing. Okay. Okay, so what I'd like to say is this thing here, OD. See, this is confusing notation. But this is completely standard notation. Given a divisor, you're looking at the meromorphic functions which have divisor bigger than minus that. On an open set U, this defines a sheaf. So in other words, U goes to the set of meromorphic functions whose divisors are bigger than or equal minus D. Okay, now this will become clear right now. Okay? So let's just take one point. So let's take D equal to N times P0, where P0 is a point, say, in some Riemann surface. So here's a Riemann surface, maybe it's compact, and we have some P0. Okay? And now you take a disk around P0. Okay? And so we identify this disk with the unit disk, delta, which with P0 going to 0, in the usual z-plane. Nothing. Okay? And now let's look at what this thing is. OD of say x. These are the meromorphic functions on x. So that the divisor of this meromorphic function, let me write m here so that consistent with the other notation. The divisor of this meromorphic function is bigger than or equal to minus d. That happened because of this identification, right? So that means bigger than or equal to minus n p0, and that means, you see what that means? In local coordinates here, meromorphic functions here are, of course, sums of Laurent series from some I don't know, some minus k, I don't care, so some
But finite in the slits.
yeah, I don't know, some n, so some number that depends on n, a n z to the n, right? And this is equal in the lingo of complex analysis to the principal part, which is the negative stuff, so a minus n, z to the minus n, all the way up here to the place where you're going to get a residue, a minus 1z, plus holomorphic stuff,
minus 1 all over z.
minus 1z. Okay? That's what it is. Right? And now look what this statement is. This statement is, this is the, so I'm going to call this star. So star is now the meromorphic functions such that when you look at them here,
And p0.
so this meromorphic function of z has a Laurent development which starts, this could start even, this maybe is 0, I don't know, but starts here at minus n. Okay, so if I'm asking for a global section of this line bundle, it's the same thing as asking for a meromorphic function which is holomorphic everywhere except at this point, right? Because otherwise, you see, otherwise, this is the only point where you're allowing poles. Otherwise, this thing has to be holomorphic, so it's holomorphic everywhere, and this principal part should be no worse than what is allowed, namely minus n. Okay? So that's a very non-trivial thing. We're interested in the global meromorphic functions whose poles are no worse than that. Okay, so sections of the line bundle, very non-trivial thing. Okay? Yeah, you don't look too happy.
No, I understand what happens locally, but how do you extend it afterwards?
No, I don't say extend, I just say the space of sections is exactly this. That's all I'm saying. There might not be any sections. That's the point. God only knows what the space of section is like. The best we can say about it is it's at most n-dimensional or something like this. Right?
No, but these functions are defined only around p0.
No.
Where are they defined?
No. The set of n meromorphic on x so that the divisor is bigger than this. This set, I confuse you. By this I mean m restricted to this coordinate chart. Say this coordinate chart.
Yeah, that's what I was saying. So how do you extend it? So or you don't care about how you extend it?
Let's start again. This is confusing. Somebody hands you a section. You go through this whole thing. You say, okay, it is identifiable with a meromorphic function whose divisor is bigger than minus n. It is globally defined. It's not a matter of extent, it is.
Okay, so you restrict it.
And now, that's what I just said here. Really, I restricted, didn't say, I'm sorry. So I restricted to this.
But there may be no such.
There may, generally speaking, probably not. There may be none. Right?
Well, I asked myself a question of existence. That's why I started the other way around.
No, this is in some sense only a formalism, right? I'm looking for a good formalism to understand, and I'm explaining what line bundles really mean also. The sections really mean this. I mean, it's really a deep, complex analytic meaning. Okay? Of course, this is in one dimension, but it's a higher dimensional thing. Okay, thank you for your patience. Okay. And now, a first exact sequence. So, let's look at the sheaf O. Let's say, let me take a divisor which is positive. For example, the one I just took in the one-dimensional case. And now, I want to look at the following first map. Okay, here we go. I mean, this is all now starting into a cohomological formalism where we can really do something. This is the sheaf of germs of holomorphic functions. Okay? This is the sheaf of germs of meromorphic functions. I mean, I did it again. Here, you see. On every open set, this is the space of meromorphic functions, which on that open set have divisors no worse than minus d. Okay? So, this is a sheaf of meromorphic functions whose divisors are no worse than minus d. Well, a holomorphic function is certainly no worse than that because this is positive. That means that these things only have poles. So holomorphic is okay. This is the sheaf map. Now you take quotient sheaf. I call this, I can't remember why I call this tau. I think because in my back of my mind, in one-dimensional case, I have the word torsion, but T, I mean. I'm going to call this TD. So this is simply a definition. This is simply the definition of the quotient.
So the second map is just an embedding.
This map,
No, the second one.
this map,
Yeah,
is just an embedding. So exact sequence means with a 0 here that this is embedding. With a 0 here, this is just a surjection. And this is also stupid, it's just a quotient. Okay? So this is a quotient thing, but a quotient sheaf. That means at all levels
That's
of
by
the
construction exact sequence. That's by construction.
By construction, this is an exact sequence. This is a completely stupid thing. Now please, let's do the concrete example. Where D is equal to NP, N is positive, on X, which is the Riemann surface. Now here's the Riemann surface, and here's this point P. And now, outside of P, the condition is, this is the sheaf of germs of meromorphic functions whose divisors are bigger than or equal to minus P, but outside of P, this means holomorphic, right? Because you only allow poles in P. So it means it's holomorphic. So outside of P, this injection is an isomorphism, right? So if you take an open set outside of P, this stuff is an isomorphism. So at the stalk level, you kill all the stalks here except P. But here, over P, it's not an isomorphism. And this is then the stalk of this quotient sheaf here is positive dimensional. You see it? Right? And you see exactly what the stalk is. It's the principal parts of this development, right? That's what's allowed there, right? And so you see what this is. This is isomorphic to Cn. Cn, yeah, Cn. Cn. You see all of these free coefficients here that you're allowing here. So that stands up like this. And this is what, okay. In English we call this a skyscraper sheaf. Because it's standing in the middle of New York City and it went straight up. Okay? So, okay? So outside it is 0. Somehow I don't know how to do it. It's the 0 sheaf outside. 0. And here it's a jump up skyscraper sheaf. Okay. That's a fundamental exact sequence. I want to mention, I've planned what ones I want to mention. I want to mention 4 or 5 exact sequences.
I think this is the best example. Like, this made me understand what a sheaf is. Like, because it's...
Yeah? That's a good example, yeah. Okay, let's do some other examples. So, not so much with divisors. Here's one without a divisor. Let's have some fun. This is the constant sheaf. Okay, constants. Integers, so, yes. I can visualize this inside of the sheaf in terms of holomorphic functions. It's completely obvious. And I have the exponential map. So let's say exponential of a function is e to the 2 pi I f. And this goes to O star, and locally, you see, for a sheaf to be exact, it means it's locally exact, right, in the limit, right, in the direct limit, it is exact. So this means only locally exact. So it's completely clear that if you have a non-vanishing holomorphic function, you can log it. And so this is surjective, and the kernel of this map are the constant functions. It's a fundamental exact sequence, okay? Let's see if we can get another exact sequence going here. Okay, here's another one.
Can you please explain again why it's subjective?
What?
Can you please explain again why it's surjective? Because it looks quite periodic when you get it.
You mean this thing here, you're worried about this being subjective or not, right?
Yeah, because, I mean, why do you put the 2 pi I there?
Yeah.
Because it gets periodic.
Well, this 2 pi I meant so that the kernel of this is the integer.
Yeah, I understand. Okay, I get it for that, but doesn't it get periodic at the other
Okay,
side?
so I know what you're worried about, so now we need to really talk about it. Okay? What does it mean that a sheaf map is surjective? It means that it's surjective at the local level, right? At the stalk level. That means,
At the German level.
that means it's at the germ level.
Okay.
That means you need to check it locally on something, whether, right? So every germ, so given x, you have a germ at x. You take the realization of that germ in some small neighborhood that you like. Take it so that it's a contractible neighborhood so you're not afraid of log.
Okay.
And then you take log. And that's it. That's proving subjectivity, okay? Okay? And of course the kernel is the constant sheaf. Here's another one. This is an important one. Okay, I'm now going to introduce a new sheaf. Let's do this in dimension n. And these mappings are D. And
Is that 3 there instead of K?
it certainly is. Thank you. And now what this means, omega k, this is the sheaf of germs of holomorphic K forms. Okay. And I mean by this, an element here, say omega is a K form. You write it in local coordinates. Holomorphic means you write in local coordinates Fi dzi, where I is length K, and where the Fi is the holomorphic in local coordinates. Okay. So you have holomorphic 1 forms, 2 forms, 3 forms, 4 forms, and so on. Okay? It's completely clear if you take the differential.
But isn't it just the Durham sequence?
This is the this is the Durham sequence restricted to the holomorphic forms. Okay? And you can check that using the Poincare lemma that we know for the Durham sequence, that this is really exact at the sheaf level. This is exact. So this is exact at the sheaf level. I'll say it again what it means. It means you take a point, and you take a good neighborhood around that point that you like, and then you check that you have a Poincare line. Okay? So in one dimension, everything stops very quickly. This is very important. You just have this short exact sequence. Okay. So let's see how many. I promised myself I would give you a lot of examples. So this is fundamental from the point of view of divisors. Here's another example. Let's look at the, now I'm going to make you crazy. Let's say div x. Okay. This is the sheaf of divisor. Okay. So what is a divisor? Let's go through it again. A divisor on U, we know what it is, right? So, I mean, here, I'm getting tired of doing this, but I think it's so hard at the beginning to get used to it. These are simply the Cartier divisors on U. Okay? You have a restriction, you have everything you want. It's a sheaf. So you have the usual thing. That's great. So, now let's think about this. Locally, I give you a divisor, we talk about this all day. This divisor is defined on some covering. Locally, it is a meromorphic function, or if you shrink it small enough, right? Okay? And so that means that this map, that there's a map that, and not anywhere identically zero, right? I mean, that's completely clear, the invertible meromorphic function. So locally, there's a surjective sheaf map, and of course, the holomorphic functions are the ones that define the zero divisor. Okay? So maybe I should put X everywhere here. If I'm not sure where I am, I put the X down there. So I would like to talk about this.
So,
Yeah.
the second map, from M to div,
Where are you? Here?
from M to the
Yeah.
divisors, it's just, you have a global thing, and you look locally at it, and you see, and you define divisors from the global thing. That's what you do? Because
Okay,
I
so-
don't see what is it exact. That's what
Yeah. I think we really need to, this is a good thing to think about now. Okay? Because I'm obviously trying to go through this.
Is it because of the definition of zero there?
Okay, so the first thing is, no, the first thing is that I haven't defined divisor to the end. Okay? Now, remember I took a covering, and meromorphic functions on a covering, right? And so on. That's one divisor. Now, that depends on the covering, of course. Right? So another divisor may be defined on another covering. Okay? Yeah?
Just some specific question. So suppose B is less than 0 in the top sequence over there, and I switch O and OD, would that make some kind of interesting output?
Yeah, very good. So before I go to this thing, let me answer Thane's question, okay? Thane, I think what Thane is asking is, let me just answer it here, okay? I know exactly what you're asking. It's great you guys ask these questions. I'm just thrilled to death. So, and then I will go back to answering your question and so on. This will take some time, okay? Okay. So above, I'm going to repeat what I wrote above. I took D positive, or maybe 0, and then I have a map here, because here I'm allowing poles at certain points, and here not, but I mean, that's okay. And then I have a quotient sheaf, which is just a skyscraper sheaf. It's a sheaf supported on the support of the divisor D. Okay. Now, this is what Thane is interested in. Let's take the other way around, for example, that. I think that's what you're interested in. Of course, you don't have this map, okay? But you have it the other way around. Also quotient, some sort of quotient. Right? Because if this is less than 0, then minus D is positive. It means you're requiring these things to have zeros of a certain order or more. So at the sheaf level, they will be holomorphic. There are no poles, right? So this, you're looking at stuff here. For example, let me take this example. Let's take the example minus NP. Right? So in the coordinates I wrote over there, let's see what I'm requiring. This would be zeros of at least this order. So if I have here a germ defined near the point P with the usual coordinates.
A and Z to the n. It will start with A and Z to the n.
Exactly. Exactly. It starts here from n to infinity. AK. Yeah. Okay, it's the other way around. So you have to watch out which way it goes. Now, I think that answers your question completely, right? Or not?
I just wonder, would it create some kind of association between T of D and T of minus D? So
Oh, these.
would they have any good relation? No?
Well, yeah, absolutely, because say in dimension 1, there's simply the isomorphic. Say here D equals NP, and here D equals minus NP, you will get absolutely the same sheaf. It's just that the exact sequence gets turned around, and it really is important that it gets turned around. Okay? And now back to what we're just talking about, okay? This is what I was just talking about, this sequence here. Let's put X's everywhere. I think what Mihai was worried about is this mapping here. The kernel is clear, that's just no divisor and so on. So it's really this mapping here, okay? Okay.
That's not really correctly defined yet. I mean, you need a covering to define it somehow. You need to fix the covering.
Okay. This is, yeah, I want to really go through this, but you're absolutely right. You've got to think more carefully than I described it here. Okay, first of all, you must agree. You must not agree anything. You must agree I was very sloppy here because, of course, on different coverings, you could have different divisors, and it's possible that you take a refinement of the covering and you refine the meromorphic functions and so on, and they can be the same. So really what a divisor is an equivalence class of divisors on coverings where equivalence is modulo refinement and so on.
Yeah, but I think this is really easy in one dimension. If you go to two dimensions, it's already-
Same thing, exactly the same thing. Because you have this restriction there. It's exactly the same thing.
And it doesn't matter if the things are discrete on the surface. Like on one dimension, they will definitely be discrete because they're points. Like the divisors will be sum of discrete.
No, let's do it. I mean, come on, you have something on U alpha. Okay, some M alphas. And now you have some other U alpha hat. And an alpha hat. And now we take a refinement of this cover, which, okay, so now I have to get the thing right. Here's U alpha. And, I don't know. U beta, I should really here have beta. U beta hat. Alright. And now I have a cover, which is compatible with all this, for example here. That's what you're worried about. Okay, so this is, I don't know, V gamma. And now you have the refinement mapped to here. So you have the restriction from, for example, of the hat, so hat. Restriction from U beta hat to V gamma of M beta hat is required to be equal, we have to talk about what that means, to the restriction from U alpha to V gamma of M alpha. And this is a problem. I think that's what you're worried about.
I don't know if I'm worried about it.
No, come on. You have the M alpha is defined here, the M alpha beta hat's defined here. You make a refinement of the cover to an open set here. And then you want to say that the restricted things are equal. Now the way I've written that is stupid. Because they're not equal, it means the divisor that they define is equal. So it means that the ratio is a nowhere vanishing and holomorphic function, right? Okay, so equal means, in the sense that this thing, this ratio, okay, I don't need to define the ratio. So this thing, I don't need to write a ratio, I could just, this thing, M beta, is equal to F, I don't know, beta alpha of U, restriction U alpha to V gamma alpha, where this thing is nowhere vanishing holomorphic. I mean, there's no way around it.
When the thing is compact, I believe this is really easy, but when it's not compact,
What do you care? Where did I use anything about compactness?
I mean, I believe that the intersections should be good intersections, not horrible.
It's just an intersection of two open sets.
Yeah, but what if more open sets intersect here? You don't care?
Yeah, no, all sorts of, this covering is a refinement of both coverings. So, it's no problem, really. You just, it's okay, really. Okay?
So is it the same as saying that if you look at the associated ray divisors, then they are equal?
Okay, that's very good. If this thing is smooth, that's a good point. It's much more intuitive in some sense.
Okay.
Right? What Kayvon was just saying, in the smooth case, is very intuitive, what you just said, in my mind. So a smooth case, you have a Cartier divisor, same thing as a Ray divisor. That's a polar set with multiplicities everywhere. And a zero set with multiplicities everywhere. And you don't care what functions define it, don't you?
Just
Right?
add the values of it.
Hmm?
You just add the values.
You just check whether the two things are the same, right? And so I think you're right, Kevin, it's much more intuitive.
So, but I mean, in the case that X is not smooth,
Then you have major problems. Second of all, you need to get a sheaf. Okay, so I really want to get the sheaf, where did it go? Oh, I really want to get the sheaf of divisors. And now you see, it's really defined by functions. So I easily get the sheaf of divisors.
Right.
You see what I'm saying? There's a big advantage with these Cartier divisors. Okay? And now getting back to the exactness of this. The exactness is, what does it mean? At the stalk level, again, let's say, at the stalk level, what does that mean? Thing gives me a point, and a divisor, a germ of a divisor at that point. That means there's an open neighborhood where it's defined as a divisor. I want to say it comes from a meromorphic function. However, I'm only caring about the point. So I'm allowed to take it as small as I want because I'm talking about it at the germ level. But this was a divisor here, and it is defined on some cover. So it is defined as a meromorphic function on some neighborhood at that point. So it's purely formal that it comes from a meromorphic function. Is that okay? Okay? So you just have to go this back and forth from sheaf to global. I mean, it's not very global, it's just a little bit global. Okay. Then we have another one. I will dedicate this to my German friends. H is the sheaf of germs of principal parts. Oh, I see. H. Nobody would understand. In German, these things are called Hauptteilverteilung. So it's the word for principal is Haupt. So Hauptteilverteilung. So maybe let's call this P, script P. But that's not Weierstrass. Principal part. I guess this is principal. No. Is this principal AL or LAC? Huh?
I don't know, it's like the Paul.
A, with A.
It's with A.
A, yeah. You got it. Yeah, the main essential part should be AL, right? Okay, so look at this. It's the same thing. Okay? Now what does it mean, principal part? It means that the negative part of the Laurent series is given in one dimension. So, okay, it means that locally you have a meromorphic function that goes onto it, locally, right? And the kernel of this thing is the trivial principal parts, is the holomorphic functions. Okay? So here, we have, this is given by a collection of meromorphic functions, right?
Does this sequence split?
What?
Does this sequence split?
No. So none of these things, maybe in some, there's a point here, sometimes in some completely formal way they split. I mean, you know what I mean, just some highly unnatural mapping you might find. But yeah, that's a good question, I don't know. So, what is a principal part? It's a principal part so that the collection of meromorphic functions, so that not the quotient is well defined, but the difference is well defined. You get it? Right? I don't care if it pulls a zero, I just care about the Taylor series part. So the difference has to be holomorphic. Okay, that's, so to speak, the trivial principal part. So
It's just equivalence class.
what?
It's just equivalent. I mean, P is a set of equivalence classes.
And P is a set of equivalence classes.
Modulo the holomorphic functions.
Exactly. Exactly. And modulo refinements, I'm sorry to say, and all of this stuff. I mean, right? Because you don't want to say on a fixed covering. So, again, you have this exact sequence. And of course, locally, again, by definition, something here in the sheaf level is at a germ. It extends to an open set as some principal part distribution. But if I contract that open set smart enough, that thing is really given on it, one piece of open set, so it's really given by a meromorphic function. That's surjective. And of course, as just what Mihai just said, this is the definition, in some sense, this is the definition of P. The meromorphic germs modulo holomorphic function. So these are fundamental exact sequences. Here's one, principal part exact sequence. The divisor exact sequence. Right? And I like very much these sequences here. These are extremely useful sequences where the skyscraper sheaves occur. This is what we call, I mentioned this, you immediately saw the Durham, and this is called holomorphic Durham sequence. I guess that's about all I wanted to introduce these examples of exact sequence. How are we doing on time? Pretty close to the end. Well, we started a little bit late, so I want to do one more blackboard. So, I just want to make one more remark. And I want to see which remark I would like to make. Let's consider a section of the principal part sheaf. So the notation that you will see is some section S. We use this is not a bundle, but this is still the notation we use for section. T. Okay. So this means that on a covering S I, so on a covering UI, SI is the principal part. So has a representative, is representative, let's say the section S is representative, so it's a section, by a meromorphic function, mi, meromorphic on ui, with compatibility. I mean, it has to be compatibility. Section here is always a covering where this thing is locally representable by definition of this thing, is represented by meromorphic functions on compatibility. Compatibility means this. Mj, please always write it this way, Mj minus Mi. For some reason you should always take J first or beta first. This difference, which we define to be Fij, the statement is the principal parts of these things are compatible. That means the difference is holomorphic. principal parts are compatible means that we don't care about the holomorphic part of the Taylor series, we just compare about the principal part of the Taylor series. So the difference, this difference is not zero. I mean, this does not define a global function, but it defines one of these Fij's. Okay? Now, two things. One, suppose that Fij, so I'm going to write it slowly, there exist functions Fi on Ui, or every Ui, such that Fij equals Fj minus Fi. It looks like I am stupid, right? So I'm assuming they're defined in terms of meromorphic functions. But let's suppose, in fact, this difference is the difference of holomorphic functions.
But can't you just add a constant and subtract a constant or something like that?
I could, but I've got to get Fij. Oh, this is not unique at all. Just some. What I just said to me is I agree completely. I think this is what you said.
No, like,
Right?
no, but if Fij is holomorphic, oh, you want to have it globally on Ui, okay.
Yeah, this is the point.
Yeah, you don't want to have it globally.
So I should have drawn the picture. This here is Ui, and this here is Uj, and here we have this thing Fij, and somehow we can't extend. I mean, Fij may be terrible, but maybe we can write it as a difference of two things. Yeah? Let's just suppose that for a minute. Look what happens. It says that Mj, I'm going to do this very slowly so we don't get confused. That's Fij, but on the other hand, this is Fj minus Fi, and this says that Mj minus Fj is equal to Mi minus Fi. This says that I have defined a global meromorphic function, and this says I have defined a global meromorphic functions with principal parts given, because I only adjusted these MJs by homomorphic things. Okay? So, if so, then there is a global meromorphic. So, if this.
Can't you identify it with something? You can identify the section with something.
Yeah. If so, then there is a meromorphic function. Let me write it down. M with principal part S. We just did it. Now let's get a little notation going. Let's get a little notation going. Watch. We have a short exact sequence. Where the heck is it? It's gone.
No, it's down there. It's down.
I should know it. I should know it. It's probably this one. Okay. This is a short exact sequence of sheaves. This is stupidly exact here, by definition. I mean, it's really just stupidly exact. If you look, it is easy to check that at the global level, you get an analogous exact sequence. Here is this sequence of germs of holomorphic functions to meromorphic functions. Here's this sequence of global holomorphic functions. Here's a sequence of global meromorphic functions. I mean the sections. Okay, here we go. This is the sections of global principal parts. These are principal part distributions on X. Now you're asking a very interesting question here. Given a section here, a globally defined principal part distribution, is there a meromorphic function here which goes to it? Given something that's defined on all these open things and compatible with something, is there a meromorphic function here?
And you asked the question above, if there are functions fj and fi. Which,
Yes. So let's just say if Fij equals Fj minus Fi, let's call this map something. Let's call this script P. So then S equals script P of n, or some n. And this is purely formal. Okay. Let's look at 2. Other way around. It's completely silly. Suppose, this is all really silly, but it's good to write it down. Suppose there is an m which has the right principal part. So principal part of m equals x. That means that m, now let's try to line this up and I'll get it right. m minus, here we go, mi minus m, do I want to do it that way? Yeah. Equals fi is holomorphic because they have the same principal part. Well, and therefore Fij equals Fj minus Fi, as above. Okay? So the only problem is to solve the problem, is Fij equal?
and is it or is it not? Is it or is it not?
What?
Does
No, in
that-
general, of course not. Sometimes not. I mean, we want to write down the instruction, right? So we want to write down the instruction. In mathematics, we always, so we have this, so we have the holomorphic functions, exact, into the meromorphic functions, exact, into the, I mean, this is okay, exact here in the middle. This is the map I just talked about, principal part. And you're interested in what that is. Because this mapping, you're interested in the kernel of this mapping being the image of this mapping. So the kernel of this mapping should tell us what principal parts are globally defined. So this mapping somehow or another goes to some problem like this. So this is the beginning of the end of a big cohomology theory. And so, for example, we want to define the one cochains for a covering, say for a sheaf S, to be equal to the set, so sets of Fij, so I call them F here because of those blocks, defined on where Fij are sections on Ui intersect Uj. So just as above, with they will be all, they're alternating cochains. So Fij equals minus Fji. Okay, that's the only condition. And now we have a boundary mapping, which comes to us by Stokes, as always. So we have the boundary mapping into the zero, into the two cochains. which is instead of Fij here will be Fijk. So the two cochains will be defined on threefold intersections. And the boundary of this thing, let's call it F, the boundary of F at Ijk, I'll write it down, is you remove I and you get Fjk, you remove J and you get, I may be off by a minus sign here, Fik, and you remove K and you get Fij. This is the boundary map. It's an alternating boundary map from here to here. And obviously these things satisfy this boundary condition. And the check cohomology here of the covering with S is the kernel of this boundary map minus the image of this boundary map. And now the image, I haven't said what the boundary map is from here to here. And so this is a zero cycle, so this thing here, F, will consist of just things on the individual things, and the boundary of this thing at Ij is Fj minus Fi. It's a very, very fast introduction, I apologize, but it's a good beginning. You see what happens. You want to introduce a cohomology theory so that kernel modulo image is a cohomology, that you're asking which stuff in this kernel is in the image. You want that to be to zero. We're very interested in getting some map here where the kernel is the things that come from here. Right? So the kernel should be the problems that we can solve like this. So it says that these guys have to be, if you take this as a one cochain, this boundary better be zero. Well, that's a trivial thing here because the way it's defined, this will automatically be zero. That's great. So the things that you get here are automatically zero in the boundary mapping, and you're asking whether they come from something. Well, it's asking the question whether they're represented as the question is whether this is represented that way. Okay, I'll be very precise about this in the morning, but I mean, what we have to do here, we have to look at coverings, we have to look at the obvious boundary mappings. It's always this alternating thing, and it's then perfect. We have so-called long exact sequencing cohomology. And just to tell you where we are going, I mean, you see it's a beautiful thing, is what I very briefly introduced you to, and I'll go through it in detail tomorrow, is the first step to check cohomology, namely what I just said. That the exact sequence then extends. So this part is exact, it's stupid. Holomorphic functions, meromorphic functions are interesting map into principal parts. And then, as usual in cohomology theory, you have a going up mapping into the first cohomology, which is this thing. Of O, so it starts again, and then it's stupidly exact here, and then you have another going up map to H2 and so on. But the interesting map is really this one here, because the kernel of this map, this is exact sequence, so the kernel of this mapping is exactly the principal parts which come from here. So what you really want to understand is this guy is really this guy and what's happening between here and here. Okay, so again, as I said, tomorrow I'll talk about this so-called Czech cohomology and the associated long exact sequence. And it's not so long. For Riemann surfaces, this stops very quickly. usually only have to go to dimension to understand. And just like in Durham, that we talked about in Durham the other class, right? I mean, the abstractions to many problems are just some cohomology class, whether something is exact or not, right? And the thing here is, it's really the abstraction, in this case, to that. Okay. So, okay, and you've heard the word Riemann-Roch theorem and so on. In case you're interested, one of the first steps of Riemann-Roch, Riemann knew this, is that this thing, you will be very happy to know, is G-dimensional. So in some sense, the abstractions to finding these meromorphic functions lie in a G-dimensional space here. And so that says somehow or another, except for a G-dimensional space somehow or another, all of these problems are solvable. That's an interesting remark. Just the finitenesses. These are finite dimensional, and in fact, by Riemann-Roch theorem, we will see that this is G-dimensional. Okay, so I think I should stop. That's way too much, but I wanted to give you some outlook.